In chapter 15.1, we're going to look at vector fields. A vector field over a plane region R is a function f that assigns a vector to each point in R. So we have a planar region, so these are the standard xy plane that we're used to for right now. That gives us an ordered pair x and y. If we plug x and y into this function f, what we get is a vector that's associated to that point. Similarly, we could have a vector field over a solid region Q in space. So now our points are in 3 space, x, y, z. We plug in a point in 3-dimensional space, and that point that's in the solid region Q will have a vector that's assigned to it. We know that there's infinitely many points, so it's not going to be possible to draw every single value or depict every single vector within a vector field. But what we can oftentimes do is get a good idea by what the field looks like by sketching several representative vectors whose initial points are at x, y. One example that we've seen previously in the class was the gradient. The gradient is one example of a vector field. For example, if we have, let's say, the function f of x, y is equal to x squared plus y plus 3xy cubed, we remember that the gradient was equal to the partial of f x with respect to x times I plus the partial of f with respect to y times j. So if I calculate the gradient here, the gradient is a function that would assign to each point x, y in the domain of the region defined where these partials exist. We would get the association to a vector. So we plug in a point, and we would get a vector field out. So the gradient actually provides a vector field. Furthermore, we also know what the graphical interpretation of this is. The graphical interpretation of this field is a family of vectors, each of whose points is in the direction of maximum increase along the surface, whose equation is z equals f of x, y. The same thing would work in 3-dimensional space. The gradient of the function f of x, y, z would also produce a vector field in space, corresponding to each point in a region, x, y, z. We plug it into this gradient, and we would get a vector in 3 space. We say that a vector field f of x, y, z, which is given by these component functions m, n, and p, is continuous at a point if and only if its component functions m, n, and p are continuous at that point. So keep in mind when we're looking at this f, this is a vector valued function. It's given us a vector. The m, n, and p, which are the component functions, these are real valued functions. And the vector field itself is continuous if each of the component functions is continuous at the point. Vector fields come up a lot. There's tons of physical examples of these things. Things like velocity fields, gravitational fields, electric force fields, things that involve flows of liquids or any kind of viscous things will be examples of vector fields. For example, we could look at a vector field of a rotating wheel. Let's suppose we have a wheel that's kind of rotating like this. One of the things some of you might realize is that in terms of linear speed, the further out on the wheel you go, the faster your linear speed is, because per rotation, points on the outside move a greater distance than what points on the inside of the wheel would move. We can also think of a vector field as diagramming the airflow around a vehicle that's driving. We also have classical gravitational fields given by Newton's law of gravitation, and there are many, many, many others as well. From electricity, we have Coulomb's law, which talks about the electric charge that a particle would face, the force due to electric charge at a point in a plane. Let's get some practice here sketching a vector field. we have the vector valued function f of x comma y, which produces the vector field negative yi plus xj. We could randomly just plot a bunch of random x and y points, plug them in, get some vectors and graph them from there. But oftentimes what's helpful is to kind of do them in batches by plotting some points and some vectors that have a constant magnitude. For example, if we think about where certain vectors in this vector field would have constant magnitude at, remember the magnitude of this vector would be the square root of the sum of the squares of its components. That would be the square root of x squared plus y squared equals to c, which would give us the equation of a circle. If we square both sides, we get x squared plus y squared equals to c squared. So on this circle, all of those points would have a vector of the same magnitude. For example, if we take c to be equal to 1, that would give us a circle of radius 1. I can pick some points that would be on this circle. For example, if I pick the point 1, 0, I plug it into here. When x is 1 and y is 0, this would be 0, and we would get j. So we have the vector j at 1, 0. 1, 0 in the point plane is right here. And the vector j we know points up with a magnitude of 1. If I plug 1 in, 0, 1, then we get negative I out. So at 0, 1, which would be right here, we have a vector that's pointing in the negative I direction, namely this way. At negative 1, 0, when x is negative 1 and y is 0, if we plug that into our vector field, that would produce negative j. So at negative 1, 0, which is here, we have a vector that points down with magnitude 1. And at 0, comma negative 1, I would get the vector I. So that would be going just down 1 unit. We get a vector that points in 1 to the right. We could do this for other values. I could look at, for example, the lengths of vectors along a circle of, let's say, radius 2. And you would see that any of those vectors you would pick would all have the same magnitude. Likewise, vectors on the circle of radius 3 would all have the same magnitude. Let's get some more practice. Let's sketch some vectors in the vector field given by f equals 2xi plus yj. We're going to do it the same way. Let's begin by seeing where there would be some similar magnitudes for these. So we want to know when would the magnitude of a vector be constant. That is, where is going to be the square root of 2x squared plus y squared equal to a constant. We would square both sides, and then hopefully we all recognize this. This would be the equation of an ellipse. To put that ellipse in standard form, let me do that. We would have the following. So that ellipse, I believe it was 4x squared plus y squared equals to c squared. Yes, that was correct. We can go ahead and divide everything by 4. This would give us x squared over 1, which I write like that for a moment, plus this is going to be y squared over 2 squared. Actually, excuse me, no, we want to divide it by c squared. Divide everything by c squared, you would get the following. This is going to be 4x squared over c squared plus y squared over c squared equals to 1. Trying to put it in the standard form of an ellipse. This would be y squared over c squared equals to 1. And then this thing here would be c over 2 squared. You can check the algebra, but that's what it would work out to be. So for fixed values of c, we're going to get a ellipse c over 2 is less than c, so the major axis would be vertical. In other words, this would be a parabola that would be longer than, not parabola, ellipse, excuse me. It's going to be longer than what it would be wide. This would be centered at 0, 0, by the way. So this would be c, c, negative c over 2, and c over 2. So just as we said a moment ago, you would see kind of like those vertical style ellipses. And at any point along that ellipse, all of those vectors would have the same magnitude. You could pick a couple of them and kind of plot them. For example, at the point, let's say, let's do 1, 1, 1. At the point 1, 1, we would have the vector 2 plus j. So at 1, 1, if I go over 1 and up 1, I would have a vector that would be pointing 2 to the right and up 1, which would be this one right here.